Okay, so I put on the screen there a summary of exactly what we have just said. As we increase the number of samples, it should be that the sample mean approaches the population mean, and the probability for all other samples reduces to 0. In other words, the spread of the distribution approaches 0. Okay? So once you get this idea in your head, the rest is actually really straightforward. So can I have your attention on this question here? So slide 47 if you're following along. Crunchy caramels, a type of sweet, are known to be normally distributed with a mean of 50 grams and a standard deviation of 3. Now, if you define the random variable x, so let me get rid of this, if you define the random variable x as the mean of, or as the weight of those crunchy caramels, then can you define the distribution for me? Are you happy it's just going to be x, it's going to be distributed using a normal distribution with a mean weight of 50 and a variance of 9, or 3 squared, because it's a standard deviation squared. Okay? So here we go. You've got x is the normal distribution that represents the weight of crunchy caramels. And you're told that x is normally distributed, so the weight is normally distributed with an average mean weight of 50 grams and a variance of 3 squared grams. Okay? So here's what I want to do. Let's suppose that I walk into a shop and I choose a crunchy caramel at random. So I just choose one of these chocolate bars at random. I want to know, what is the probability that this crunchy caramel has a mean weight of less than 48 grams? Okay? So can you have a go at that for me? Can you find me the probability that the crunchy caramel that I select is less than 48 grams? So we did this last lesson. Just a reminder of how we need to do this. We need to convert this to a standard normal distribution. Then we can find that probability which we're after. Okay? So remember, how do we convert it? So we convert it to a standard normal distribution. What's the mean of a standard normal distribution? 0, right? And what's the variance? 1. So basically trying to convert this into something that looks like this, then we can look up that probability. Make sense?
Yes.
Okay. So what we need to do, and I think this was the question which you were answering, Nikki, how do we convert that outcome into what the probability that z is less than to? So we take the 48, and what do we do to it?
-3.
Perfect. Divided by
3.
standard deviation. Good. Okay. What did this come out as?
Negative 0.67.
Perfect. Good. So it's negative 2/3. Okay. So remember, always leave it to 2 decimal places because that's the accuracy of the tables which you have in front of you. Okay. So in other words, what you're looking for is the probability that z is less than negative 0.67. That's the number which you need to look up in your table. Has anybody done that? How many? 1.4%. Okay. So in other words, the answer to this question, if I go into a shop and I select a chocolate bar at random, the probability that the chocolate bar that I select, given that the mean weight should be 50 grams and they're expecting a standard deviation of about 3 grams, is about a 25% chance of picking up a chocolate bar which has a weight less than 48 grams. Make sense? Okay. Now what if I do exactly the same, so I've got the answer on the screen now, okay? What if I do exactly the same idea as what I got you to do with the Beyonce lyrics? Instead of picking up 1, so this would be what happens if I pick up 1 chocolate bar, what happens if I went into the shop and I was feeling a bit greedy and I picked up 5 instead, right? What now would the probability that the mean weight of those chocolate bars be being less than 48 grams? So in other words, it's no longer just x, it's basically what happens if I pick up 5 chocolate bars and I take the mean of those 5 chocolate bars. What's the probability that the mean weight of those 5 chocolate bars is less than 48 grams? Well, we need to follow this idea of the central limit theorem. So central limit theorem, or CLT for short, okay, says that as you increase the number of samples, literally what I'm doing there, I'm taking 1 sample, then I'm taking 5 samples, I'm increasing the number of samples. What happens to the mean, the sample mean?
To the population.
It approaches the true population mean. Okay. What also happens?
Standard deviation.
Good. The standard deviation approaches
0.
0. Fantastic. In fact, I probably should use a lowercase s for that one. Do you remember this is talking about sample? Yeah, this is talking about sample. Okay? So the thing is, I know that this should approach the true population mean, but I don't know how far, or I need to find a way of reducing that standard deviation. Okay? So have a think, okay? If the probability of getting one crunchy caramel with a weight of 48 grams was about 25%, what should happen to this probability, so the probability of getting the mean weight of the chocolate bars being less than 48 grams, what should happen to this probability as I increase the sample size? It should decrease. Does that make sense? Because it should be that the sample mean should approach the true population mean, which I know is 50. In other words, if I go out and select a bigger sample, it should be that there's a lower probability of me getting a mean weight of less than 48 grams. Yeah? Make sense?
Yes.
Okay. So let's have a think about this then. What I can think about is these 5 crunchy caramels that I can pick up, they are all distributed using the same distribution.
Yes.
Does that make sense? So each of these crunchy caramels are all distributed using the same distribution. Okay? So in other words, x1, my first crunchy caramel, will be normally distributed with 50 and 3 squared. My second crunchy caramel will be normally distributed, same kind of idea, and so on and so on. So x3, same idea. x4, same idea. And finally x5, the final crunchy caramel which I pick up, will be distributed using the same distribution. Does that make sense so far? So each one of these, if you like, represents a different sweet. All good?
Yes.
Okay. So what happens then to this distribution? How can I combine it together into a new distribution? How can I combine it together into the mean, if you like? So this is just one, so x just represents one crunchy caramel. I want to put all of these distributions together so that it's in like one new distribution. Does that make sense? Okay. So let's have a think. Let's have a think, and it might be an idea to have a look at the screen. Okay. If I want to find this number that goes here, this parameter, that should be the mean, shouldn't it? That should be the mean. Look up here. This is the mean. This is the standard deviation squared. Okay. So I want to look here at the mean. So have a look. I've got the mean of all of these individual crunchy caramels, which are all distributed using this normal distribution, okay? And I'm going to divide it by n, or 5. That makes sense? Okay. So have a look, okay? Have a look. That's it in general. Really what I can say here is that the number that goes there should be the expectation of my random sample, so the expectation of x bar, and the number that goes there should be the variance of x bar. That makes sense, right?
Yes.
That makes sense?
Yes.
Okay. So the question really becomes, what is the expectation of this sample, and what is the variance of this sample when we put it all together? Okay? So, how do I calculate the expectation of a load of random variables? All summed together and divided by n. Plus them all together and divide by n. Yeah, because I'm literally saying x bar is what happens when you take all of these samples. So x bar is what happens when you take all of these samples, so x1, x2, x3, x4, and x5. I take all of these individual sort of crunchy caramels, if you like, these random distributions, or these random variables. I add them all together, and I need to divide by the number of variables that I have. So I need to divide by 5. That make sense? Okay. So what would the expectation of x bar be? What would the expectation of this thing here be? So have a think. I think you can do this using the expectation algebra that I've taught you. Okay? Just remind yourself what is, and I'm running out of a little bit of space here, but let's see. What would the expectation of x bar be? It's going to be the expectation of all of this thing. Yeah? So in other words, it's going to be the expectation, of x1 plus x2 plus x3 plus x4 plus x5. Good. In fact, I could just write that as 1 divided by 5 of that thing. Couldn't I? It's the same thing. Okay? Now just remember your expectation algebra. If I have the expectation of a number times by a random variable, what's that equal to?
A times B one. Expectation
Absolutely. So the expectation of that. That's the same thing. That was your expectation algebra, right?
One. Yes.
So that means that I should be able to pull, let me just write that a bit
1/5.
nicer, 1/5 out the front.
Yes.
Okay? So this should be equal to 1/5 of the expectation of x1 plus x2 all the way through to xn, in this case x5. Is that okay?
Yes.
Now what is the expectation of each of these individual things?
24.
It's just basically saying, so what is the expectation of, for example, A plus B plus C plus all the way through? You're happy that's just the expectation of each of those individual random variables?
Yes.
Okay? This is the same as the expectation of A plus the expectation of B
Yeah.
plus the expectation of C, all the way through. Yeah?
Yeah.
Now, like I say, there is a proof of that, but it's a bit gnarly, so I'm not going to give it to you. Okay? But just take my word on it, it definitely does make sense. Okay? So in other words, this is the same as 1/5 of the expectation of x1 plus the expectation of x2 plus the expectation of x3 plus the expectation of x4 plus the expectation of x5. That's hidden behind the thing. That makes sense? Okay. Now just remember, are you happy that x1, x2, x3, x4, x5, they're all the same? Yeah? So in other words, if I'm just repeating this, it's basically a repeated sum. It's the same thing being added to itself how many times?
5 times.
5 times. So in fact, I can just say, all of that thing is just 5 lots of the expectation of x.
Yes.
Yeah? You happy with that? Now just have a look. What's a fifth of 5 times the expectation of x?
1.
1 lot of the expectation of x. That okay?
Yeah.
So in other words, what I'm saying, let's just kind of recap what we've done here. The expectation of x bar, the expectation of all these samples put together, should be the same as the expectation of each of these individual random variables. That makes sense?
Yeah.
Now what is the expectation of each of these individual random variables?
50.
It's 50. The expectation is equivalent to the mean. Does that make sense? Yeah? So in other words, the number that goes here for this particular situation is just simply 50. And that makes sense, because if you remember from our central limit theorem, if you take a load of samples, those sample means should approach the true population mean. So in other words, if your sample mean is all 50, that should approach what's happening at the true population level. That should approach 50. Is that okay?
Yes.